Swayam Prabha. Digital India. Educated India.
Okay, so let's just do a proof of this. So one convenient way of writing this particular condition is to simply write this lambda star transpose Ax minus b equals 0. Now, why is this? Why can I write it like this? The reason is because I know that Ax minus b or rather b minus Ax is always greater than equal to 0. Since b minus Ax is greater than equal to 0, moreover lambda is also greater than equal to 0. So, then their inner product will be 0 only if you have this sort of situation where if there is slack in one of them, then the other one must be 0, right. So this would be a compact way of expressing this. So let me write it more neatly. So for x star in omega p and lambda star in omega d, the above condition, the complementary slackness conditions complementary slackness conditions are equivalent to lambda star transpose Ax minus b equal to 0 and A transpose lambda minus c the whole transpose x star, sorry, lambda star here, x star equals 0. Okay. All right. So, now we want to show that the necessary and sufficiency of complementary slackness for the optimality of x star. So, part 1 is suppose x star in omega p is optimal for the primal LP. So, now if x star is optimal for the primal LP, okay, is it possible that the dual is infeasible? It is not possible, because the duality theorem of linear programming, we learned that if the primal has a solution, then so does the dual, right. So, it cannot be that the dual, if you have a finite optimal solution for the primal, then you cannot have that that the dual is infeasible. So, which means that what this means is that omega d is not empty. Okay. Moreover, omega d is not empty, and so it cannot be that the dual is infeasible, and moreover there always exists a solution to the dual and the optimal values are equal. We know that from the theorem of from the strong duality theorem. So, optimal value of primal LP equals the optimal value of dual. What does this mean? If I look at C transpose, so which means that first, not only that the omega d is not empty, there exists a lambda star in omega d such that C transpose x star, which was my primal optimal value, is equal to B transpose lambda star. All right. Now, if you compare this with this strong duality statement, compare that with the weak duality statement, which is written here, then and this weak duality statement, remember, was for all x in omega p and all lambda in omega d. So, consequently, we get, by taking x as x star and lambda as lambda star, what are we going to get? We are going to get that C transpose x star is equal to lambda transpose A x star is equal to B transpose lambda star. By combining with weak duality. Okay. So, now what does this say? What does this say? What does the red statement here say? Well, the red statement simply says that now I can do the following. I can take this part together. There are actually two equations here. There is one equation here and another equation here. So, let me take one of each of them separately. So, what this is effectively saying is that lambda star transpose A x star minus B equals 0, and that A transpose lambda star minus C the whole transpose x star equals 0. Right. And now, since if these are if these have to be equal to 0, what does this mean? This means that it has to be that component wise they should be equal to 0. That means, see, remember, this quantity is always less than equal to 0, this quantity is always greater than equal to 0, this quantity is always less than equal to 0. Sorry, this is greater than equal to 0, and this is also greater than equal to 0. So, for the inner products of these vectors to turn out to be equal to 0, it has to be that component wise they are actually they are each 0. Otherwise you will not get that the inner product ends up 0. In the first case you would get that the inner product is negative, otherwise, and in the second case you will get that the inner product is strictly positive, right. Okay. So, what does this mean? This means that lambda star j times times this sum that we had here, which is times this sum, or lambda star I times this sum, which is captured in this inequality. That must be, so lambda star I times summation over j equals 1 to n a I j x star j minus b equals 0, minus b I equals 0, which means that, what does this mean? If now Aij x star j minus Bi can be either equal to 0 or can or strictly less than 0. These are the only two possibilities, which means that so if it is equal to 0, this holds trivially. If it is strictly less than 0, then the only way that you can have the product equal to 0 is that lambda star I itself is 0, right. So, that which means that if a summation a I j j equals 1 to n x star j minus b I is less than 0, must imply lambda star I equal to 0. And similarly, we can show the other way around. Similarly, sum over the sum, if this inequality holds with strictly, then the corresponding x star j must be equal to 0, right. So, this is one direction of the complementary slackness condition. What we have concluded so far is, if x star is optimal, then it has to be that these complementary slackness conditions must hold. Now, let us look at the other direction, part 2, the other direction. So, assume that lambda star transpose A x minus b equals 0 and lambda star transpose A minus c the whole transpose x star equals 0, okay, for some x star in omega p and lambda star in omega d. Now, what does this say? Well, we can rearrange this a little bit. So, the first equation simply says B transpose lambda star equals lambda star transpose A x star. Now, the second equation, it again says that, so the second equation, okay, I made a mistake in writing this, sorry. Yeah. The second equation similarly says that lambda star transpose A x star is equal to C transpose x star. All right. So, now what does this mean? This means that B transpose lambda star is equal to C transpose x star. So, the very fact that these two conditions hold for some x star in omega p and lambda star in omega d, from there we conclude that B transpose lambda star equals C transpose x star. And now, what does this mean? We know from weak duality that an inequality in this direction must hold, and if equality, and we know from the strong duality theorem that if equality holds, then it has to be that these two are optimal. Okay. So, then it follows that x star is optimal for the primal LP. and that lambda star is optimal for the dual LP. All right. So, what does this? So, this completes the proof, and what have we learned from this? We have learned basically that as far as optimality is concerned, optimality of linear programs is concerned, essentially it comes down to just. Okay, so what does this theorem teach us? It basically teaches us that if you have if you take a candidate feasible solution x star for the primal and a candidate feasible solution for the dual lambda star, they are optimal if and only if they satisfy these two equations. Now, these two equations, if you see them, they are actually not linear equations. It says that lambda star transpose something in x must be equal to 0, and likewise something in lambda transpose x star is equal to 0. So, this is the where the hardness of linear programming actually creeps in. So, the first simply checking that x star and lambda star are feasible is a matter of checking that they satisfy bunch of linear inequalities, and it is easy to generate solutions to linear inequalities. But you have to also for finding an optimal solution, you have to effectively end up solving some nonlinear equation, even though the original problem was just a linear problem. Okay. And this is the root of why this is linear programming is non-trivial. But you will soon see that this kind of nonlinearity comes up in all types of problems involving inequality constraints. The nonlinearity is in this product equation. So, the lambda star, so sorry, this was supposed to be x star. The lambda star is multiplied with this to get you, and that product, this quadratic thing has to be equal to 0. Quadratic equation must be 0. Likewise, this quadratic equation must be 0. Yes, but it is, if you look at it as equations in your variables x star and lambda star, then these are not linear equations anymore. All right. Another way of thinking about expressing the same thing is that if you look at this condition simply says that if something is true, then something else is true. It is a conditional statement. It is not merely asking you to, you cannot write this as simply a solution of linear equations. It says that if this is strict, then that must hold, and if it is not strict, then there is no particular, it says nothing in particular, right. So, this is why linear programming is actually harder than it appears, because eventually you have it at its root, even though the original problem is just involves only linear formulations, at its root to solve the problem you are ending up solving some nonlinear equation. All right. Okay. So, that is one thing, but having said that, if I gave you two candidate solutions, to just verify that they are optimal is very easy. All I need to do is just check these two, check that they are feasible, and simply check that this holds, right. So, finding one may be harder, but verifying is absolutely easy, because all I have to do is just check this, right. So, what this has done is taken a problem which is linear programming and reduced it to just simply checking some nonlinear equations, checking for the satisfaction of some nonlinear equation. Now, you will see why this is a significant simplification, because we started off thinking of linear programming saying that it must have a solution on an extreme point, but then there were so many possible extreme points, it was not easy to characterize them, and we said, well, if I gave you even one extreme point, how do I confirm that it is in fact optimal without comparing with all the other extreme points of the linear program? All of this is extremely hard to do. This in comparison is something that you can potentially do much more easily. Yes. Not necessarily, not necessarily. So, the earliest algorithms for solving linear programs were actually went about their business by searching over extreme points, just cycled over extreme points and made sure that you are getting to a better extreme point at each step, and that is how they tried to find the solution. Modern algorithms for LPs try to attack this directly, try to solve these nonlinear equations directly. Yes, yes, yes. So, effectively solving a linear program amounts to finding an x star which is in the feasible region of the primal, and alongside a lambda star which is in the feasible region of the dual. So it means being feasible for the primal and being feasible for the dual simply means that they must satisfy these linear, they must lie in these polyhedra. And but in addition to that, they must also satisfy these nonlinear equations. Right? That's what it means to solve a linear program. Okay. All right. So this particular condition, the reason. Okay, I'll also give you a bit of intuition on why this condition appears. The reason for this is that if you look at the dual variables, remember I had told you that I had mentioned this once, and this I will mention this again in later also, that if you look at the dual variables are actually the same as what we were earlier calling Lagrange multipliers. So, when we were looking at optimization problems with equality constraints, we had these additional variables which we denoted by lambda, one for each constraint. They came out of doing applying implicit function theorem on the constraint and so on. Now, those additional variables are actually the Lagrange multipliers. Now, if you look at the complementary slackness condition, what it effectively says, the complementary slackness condition effectively says that I need to have only Lagrange multipliers for those constraints that hold with equality. So that although the constraint is stated as an inequality, if it holds with equality, then there is an applicable Lagrange multiplier for that constraint. If it does not hold with equality, which means if this inequality is strict, then the Lagrange multiplier for it is effectively 0. All right. So that's what these conditions are saying, and it's the situation is completely symmetric between the primal and the dual. The variables of the primal are the dual variables of the constraints of the dual, or the Lagrange multipliers of the constraints of the dual. Okay, and likewise the variables of the dual are Lagrange multipliers of the constraints of the primal. All right. And so you can make the same claim about the dual as well. So if there is a constraint in the dual that is strict, then the corresponding Lagrange multiplier, or equivalently the primal variable, must be 0, because it does not count effectively. Okay. Again, as I said, we will see this some more as we go further into nonlinear optimization.